y, and z. And we can place the cube on these axes. I wonder how. Right, so there's the cube on these axes. And now, we want to know what is the moment of inertia tensor of this cube around the origin. So we compute each of these integrals over the cube. The first question we always ask when computing moment of inertia, when computing set of mass, when computing moment of inertia tensor, and I will be ruthless. If you get this wrong, you get naught for the entire question. The first thing we always do is we ask, what region are we integrating over? Right, that is a question that must be right. It's binary. It's right, you get marks. It's wrong, you get naught. So, what is the region that we're integrating over here? What coordinate system will we use? Cartesian coordinates, because well, the cube is a great square object. What is the region in each coordinate? Well, let's say the side length of the cube is L. In that case, we take x from naught to L, we take y. From naught to L, we take z. To L. Right. So that is the region over which we're integrating. So all of our integrals are going to look like this. Integral naught to L, integral naught to L, integral naught to L of stuff times the density of the cube dv, which is dx, dy, dz. The first thing we always do, this is a uniform cube. The first thing we always do is we compute the relationship between mass and density. If it's a uniform cube, density is constant. Otherwise, I would give you some equation for density. So the first thing we do is we say mass is the integral, simply this integral. The integral of dm, which is the integral of rho dv. And that integral is quite clearly, in this case, equal to rho L cubed. So in this case, quite clearly, it means that rho is equal to m over L cubed. Right. Now we compute all of those integrals inside that matrix. But we can make our lives a lot easier by noticing that a large number of those integrals are equal. Firstly, all the diagonal integrals are equal. Because this cube has a symmetry in x, y, and z. It doesn't matter whether I replace x with, if I swap x and y, it doesn't matter. If I swap x and z, it doesn't matter. If I swap y and z, it doesn't matter. That must mean that those diagonal elements are all equal. Symmetry under swapping x, y, and z, surely that means that those integrals are equal. Of course, if you're not convinced that integrals are equal, then don't use symmetry. Then compute everything. That's also fine. So let's work out Ixx. Ixx is going to be the integral of y squared plus z squared dm. That's going to be m over L cubed times the integral 0 to L times the integral 0 to L times the integral 0 to L of y squared plus z squared dx y dz. So, computing that integral is really just a matter of forming math. I'm not really in the mood for going to the steps. But I think that's the answer. Welcome to check me. And this is then also equal to I and I z. Now it turns out that IXY, IYZ, and IXZ are also all equal because of the same symmetry. I can swap X with Y, Y with Z, and so on and so forth. So that means that any pair of distinct things multiplied together, X, Y, and Z, should give the same answer when expressed over the cube. Right. If you don't believe it, go to Mark 7. I believe it. Of course, mathematics has done the work for me, so I know the answer to this, right? So if I want to work out IXZ, for instance, or XY, and the rest of them will be equal to this, well, that's negative the integral of xy, which is simply going to be negative m over L of xy dx y dz. And you can check my answer. Maybe Rob Barton, the mathematical made mistake. Right, so and that itself is equal to IXZ is equal to IY. So we have now computed everything we need. We now have the moment of inertia test. We can write this out. You'll notice that it is not diagonal. So my choice of x, y, and z axes as a vertex of the cube are not principal. They're not principal axes. Indeed, the moment of inertia tensor is going to be, in this case, we've got IXX, IYY, and IZZ. They're all 2 over 3 ml squared, and the other one's 1 over 4 ml squared. So I can take ml squared out. Let's take the lowest common denominator of those guys, 12. Right, so IXX is then, how many 12ths is 2/3? 4 12. Two-thirds is 4 times 2 is 8. You've got 8 there, and 8 there, and 8 there. And what about 1/4? How many times is that? Minus 3, right? Yeah, but I can to write that out. Then we can promote the inertia tensor by it. Don't ask why these conventions. They just do. Minus 3, minus 3, minus 3, minus 3, minus 3, minus 3. Right, well there's a moment of inertia tensor. That's great. What if we're rotating it around? What if we rotated the cube around the axis through the diagonal? Here's an application. An application that wouldn't be so easy to do directly. Let's rotate the cube around its diagonal axis and find out what the kinetic energy is. What is the diagonal axis? The diagonal axis is given by I want a unit vector, remember? We draw it in. This particular cube is annoying. But the diagonal axis would be this line here. From the origin out. Unfortunately, this particular cube looks like it's right next to it. So if you rotated it, you can see quite clearly. So, hang on a second. What's that? This point here is 1, 1, 1, right? And this point here is 0, 0, 0. So can someone give me the diagonal axis? Oh, you're absolutely correct. Point. Very good. Oh. Right, so what is the diagonal axis? I want you to do the vector. Come on, guys. It's an old test, but I don't see the answer straight away. I'm really thinking selected. Well, it's going to be parallel to that. Then it's going to be a unit vector. So it's going to be that. Right, the unit vector in the diagonal direction. I'm just rotating. I'm not going to explain anything. Right. So we've got this guy. And we can get the kinetic energy there, right? What's the kinetic energy? The kinetic energy is when we apply, when we make this our omega. So our omega vector is going to look like angular velocity value over root 3 times 111. Alright, so we can get the kinetic energy when we rotate around the diagonal axis simply by working it out. Kinetic energy is going to be, when we do this twice, the root 3 becomes a 3, the omega on both sides. So it can look like ml squared over 4 omega squared 111. This thing, 8 minus 3 minus 3 minus 3, 8 minus 3 minus 3 minus 3, 111. Again, I'm extremely lazy. But the answer is 1 over 12 ml squared omega squared. So we've now obtained the kinetic energy when we rotate a cube around this diagonal. Right. I believe that's where to stop for today. I think there's a lot of reading that you should be doing at this point. You should make sure you understand chapter 3 and go through it. 59 pages. Hey, I wrote it in.